So today I'm going to talk a little bit about the realization that the universe is expanding. And also use that as a stepping stone to go from, remember last time I talked about how Hubble made some key observations to show that there were actually other galaxies out there. The Milky Way was just one among many galaxies. And then the next step is that you might ask, well, what are these galaxies doing? Are they moving around? Are they staying still? And the realization that they all seem to be moving away from us. And that was the first step towards people understanding that it seems like the universe is actually expanding on very large scales. Before I do that, I wanted to take a step back and talk about an interesting paradox that was raised by this fellow here, Wilhelm Olmer. Olmer, let's see if I can play around here. No. So Olmer was an astronomer, philosopher in the 19th century, and he basically made the following observation. He said, well, people have this idea now that the universe is filled with these stars, and the stars are suns, are like the sun. And there is also this kind of lingering idea that the universe is infinite. Okay? And in many ways, this idea that people had in their heads then was similar, I think, to the idea that a lot of people in modern society have about what the universe is like beyond the solar system. I think for a lot of people, the universe is basically this random distribution of stars that are kind of scattered out, and it more or less goes on forever. The universe is very, very big, infinitely big, and that's just how things are. And if you think of it that way, it's actually pretty depressing. It's just like this endless sea of stars. But he said, well, if that's the case, if it's infinitely big and there's nothing but a random distribution of stars, then why is the night sky dark? Because if there are an infinite number of stars, no matter what direction I look, I'm eventually going to hit one. The universe is infinitely big. So, does anyone have a problem with that statement? I wonder what people think of that. Does that make sense to you?
Well, how does he know the universe is infinitely big?
He doesn't know that. So, it's possible the universe just isn't infinitely big and that it has some size. So maybe it's only this big and it's like a big ball of stars. So you can argue that this paradox is that, well, this means the universe isn't infinitely big. It's not just this endless sea of stars. There's got to be some edge to it or something. Okay. Can anyone think of a reason why this wouldn't be true? Come on. People must think of reasons why this wouldn't be true.
You don't see the light from all the stars because some of them are so far away.
Okay, that's good. That's good. So you're saying, well, wait a second now.
If it's infinitely big, like it takes light time to travel, maybe it just has a
Okay, that's another one. Okay, so you said those are two different things actually. So the first thing you said is, well, the farther the stars are away, the fainter they are, right? So maybe the universe is just so big that the stars that are really far away we just can't see because they're so far away. Right? The second thing you said is it takes a finite amount of time for the light to get to us. That's something else. But let me address that first point. Does everyone understand what that point is? That the stars that are far away, we just can't see them. Does that make sense? Okay. Well, that's a good point. It turns out that's not right. Okay? And the solution to this paradox is not that the stars that are really far away are very dim. And that's the first thing you think of. So that's the first thing a thinking person thinks of. That things that are far away are dimmer, and therefore we just can't see them. But it turns out the numbers don't work out. And this is what Olber realized. This was the thing that Olber did that made him realize that this is a conundrum. Okay? Because what happens is, remember that if you have, let's say we're here, in the middle, this is us, and we're looking at a star that's way out here. The light from this star, the brightness of this star from remember, falls off like the distance to that star squared, because the light spreads out over the surface area of a sphere. So the light's going out over a sphere, and its dimness, it's getting dimmer and dimmer, like 1 over the distance to that thing squared. Right? But now, as we go out in radius, there's more and more stars at that radius. Because the volume of that sphere is growing a lot that we're going out to. So while it's true that the light from this star is dim, there are a lot of other stars that are roughly at that same distance compared to stars that are nearby. So while the light might be 4 times dimmer, there are easily 4 times as many stars at that distance. And those two effects cancel out. And you never win. So you can't win by going to things that are farther and farther away, because as you go farther and farther away, there's more and more stars in every ring that you go out to. Does that make sense? So it cancels out. The effect completely cancels out. And Olber realized that because of this, if there were infinite, the universe was infinitely big and there was just an infinite number of stars out there, no matter what line I pointed at in the sky, it ought to hit a star, and it ought to be very bright. And he calculated that the night sky should be basically brighter than the sun. It should be brighter than daylight at night. And this is true. So this is considered a paradox. Okay. Now, what are some solutions to that? So we had one solution. The immediate solution was, well, maybe the universe just isn't infinitely big. Okay. So if the universe isn't infinitely big, I can't do this. It's got to have an edge. So if the universe stops at the edge of this square, then I don't have to worry about it anymore. But certainly in the night, yeah.
Well, who makes the statement that Zoom interacts? Well, what's at the end? There's a big wall there.
Well, that's the thing. So then you start getting to, well, okay, well, if it ends, what's that all about? Like, what's, is there a big wall? Is there an edge? You just, is it like Columbus and you fall off the, There be dragons out here, what's going on? So, right, so that's a question that's raised. And the other point, and this was the thing you were coming up with, the second point is, well, there's another possibility there. Here's 3 possibilities that I'll list. This is something that's sort of in between. That the universe has a finite, infinite size, but there are only stars nearby. And that's kind of a similar thing. That the universe is infinitely big, but for some reason there's only stars near us, and everything else is dark. That seems also kind of weird. Why is that? But the final thing is, even if the universe is infinitely big, but it is of a finite age, then you can't see stars that haven't had time that their light hasn't had time to reach us yet. Okay. So let me give you an example of what this is like. So imagine that we have the current universe. And, the nearest star to us is Alpha Centauri. It's like 4 light years away. There's other star clusters that are 8 light years away, etc., etc. And the light from the center of the galaxy is, 25 light years away. And imagine that God comes in and just shuts the lights off. Boom. Everything gets shut down. So the universe goes dark. Okay, and we wait a really long time, and now we turn the universe on. Click, all the stars start shining at once. What does the world look like? Well, it would be dark. 8 minutes later, the sun would light up. It takes light 8 minutes to reach us from the sun. A little while later, we'd start seeing the planets light up in the sky if it was dark. Okay. 4 years later, we could see the light from Alpha Centauri. 8 years after the lights are turned on, we see the nearest star cluster. 25 years later, 25,000, I said it wrong before. 25,000 years later, we see the center of the galaxy light up. 2.5 million years later, we see Andromeda in the sky, etc. So there's a time it would take for all the light to get to us. And so if we just haven't had time to see all the light from all the galaxies in the universe, even if it's infinitely big, the night sky would not be dark. Because there's still light coming at us. Does that make sense? Any questions about that? So the modern solution to Olber's paradox is we now have pretty good evidence, in fact, quite good evidence, that the universe has a finite age. And in fact, we actually know what that age is. We think the universe is about 14 billion years old. So even if the universe wasn't evolving at all, we couldn't see anything that was more than 14 billion light years away, because the light wouldn't have gotten to us yet. The other thing that's going on in our universe is that the universe is expanding. And when the universe is expanding, that also helps explain the darkness of the night sky for a slightly different reason. But so this paradox, this Olber's paradox, sort of this lingering problem that was around for a while, is now no longer an issue. We actually now think that it's plausible that the universe is infinite, but it's just not infinitely old. And that helps with this issue. Are there questions about that? So if you remember last time, I was talking about this guy, Edwin Hubble, and Hubble had really made an amazing contribution to astronomy by showing that there were other galaxies out there. That really, if you think about the universe on the largest scales, it's not appropriate to think of it as a collection of stars. That's really not what the universe is. It's more appropriate to think of the universe as a collection of galaxies. And that while galaxies are a collection of stars, the universe on the largest scales, its fundamental units are these galaxies. And galaxies are the things that host stars. And stars are the things that host planets going around them. So it's sort of this sort of nested dolls, Russian dolls kind of thing. Remember how he did this? He had access to the largest telescope in the world, this heroic machine that was built that had a 100-inch mirror of glass. It was hauled up on top of Mount Wilson, and he was using this telescope to be able to resolve individual stars in galaxies like Andromeda. And when he did that, he showed that they're actually distant galaxies in their own right, not these clouds of gas or something else like that in the way. So he revealed that there was a universe of other galaxies. And so after that time, this is a more modern picture, but we now know, for example, that the Milky Way has these galaxies around it, these little satellite galaxies around it. And the Milky Way is a member of the local group of galaxies. The Milky Way is here. Here's the Andromeda galaxy that I've talked a lot about. And as you go out, this is about 3 million light years across, this picture. As we zoom out again to 30 million light years, every dot on this picture is a galaxy. And so it's the galaxies that are the building blocks of the universe, if you will, the things that light up in the universe, and those galaxies host billions of stars in many cases. And it keeps going. So this is 30 million light years, now 300 million light years scale. So it's even bigger. There are all these. You see that galaxies like to live in clusters and filaments on very, very large scales, as if there's structure in the universe on the grandest scales. Now, the interesting thing is, Hubble was not only able to measure the distances to these galaxies and make this map. He was able to do something else. Remember that when we're studying the light from these distant objects, we can do lots of things to it and try to learn things about the objects that are emitting the light. And one of the things that you can learn about by studying the light is the speed with which galaxies are moving away from us or towards us. And that's using this phenomenon that's similar to the Doppler shift. That light, remember, when light's moving towards you or away from you, its wavelength gets stretched or scrunched, depending on whether it's moving away or towards you. And that's called redshift or blue shift. That's a phenomenon of waves. And so Hubble was able to use the light from these galaxies to not only measure how far away the galaxies were, or estimate how far away they were, but also to measure the speed with which they're moving. And when he does that, he finds that the farther the galaxies are away from us, the faster they're moving away from us. He finds, first of all, most galaxies that he's looking at are actually moving away from us. So it's as if, in this picture here, the whole ball of stuff you see is all moving away. And so, and in fact, when he plots the velocity with which they're moving away from us versus the distance to that galaxy, he sees that the galaxies that are farther away are moving away faster. So this is called a Hubble diagram. So this is the velocity of the galaxy moving away from us. This is the distance to that galaxy. And in fact, you can draw a line through those points, and Hubble did. And if you can draw a line through points on a plot, that means you can describe it by an equation that's like, remember y equals ax plus b in algebra class? Y equals ax is a line, and a is the slope of the line. Same deal here. Here y is the velocity, and x is the distance. So we have the velocity equals something times the distance. And that something is dictating the slope of this line. But you can see from this equation that if you know the distance, you know the velocity. The farther the things are away from us, the more distant they are. And that h, does that make sense? So this is actually Hubble's original plot. And the plots that people make today are much more amazing than this. One of the things that's horrible about this plot is that there's no uncertainties on his points. So, if my graduate student made a plot like this, I'd kill them because this is not a good plot. But, he's Hubble, it does what he wanted. So this is what Hubble saw. He sees all the galaxies are moving away from each other like this. And if you recall, this is just a fascinating story. Because, Einstein, his equations of general relativity, gave rise to a universe that was expanding. And Einstein knew about this. And in response to this realization, he actually changed his equations. He added an additional term to them that we call the cosmological constant to keep his universe from either expanding or contracting, to keep it still. And he considered this fact his greatest mistake. Because in principle, his equations could have predicted the expansion of the universe itself, but instead he thought it was too bizarre. He thought this idea that the universe was changing and not ever ever present, eternal. To him, that seemed weird, just so beyond the realm that he had to change his own equations to keep the universe from doing this. And I think that says something because Einstein was a pretty creative person and willing to think outside the box. But even he thought that this was just not, it did not suit his aesthetic for what the universe should be like. And again, in much the same way where it was hard for the Greeks to imagine a universe that was so big that we couldn't see the stars wiggle from one time of the year to the next. Or it was hard for Curtis and Shapley to grapple with this idea that both the galaxy was big and there were other galaxies. It was difficult for Einstein to accept this idea that the universe could possibly be changing with time, that it wasn't ever present and always there. But the fact that now you have a universe that's dynamic suggests that space itself, that the universe itself, is not something that's always been the same. But in fact, it's evolving because we see this expansion. Now I should mention that, it wasn't just the fact that Hubble saw galaxies moving away from us, that everybody just dropped everything and said, oh, okay, that means the universe is expanding. Okay? This was just the first step. This was the first piece of evidence that let people start thinking about that. There was a lot of resistance to this idea, and there has been sort of a continual march of disagreement with this possibility, people trying to think of other things that might be giving rise to this phenomenon. Ever since this discovery, really. And I would say only within the last 10 years has it pretty much come down to maybe 0.01% of astronomers don't believe it. But almost everybody else is now, taking a really hard look at all the evidence that exists and suggests this is what's going on. And so there are a lot of other pieces of evidence that this is what's going on, but this was the first piece, and one of the easiest pieces to sort of look at and kind of get, okay, I see what that means. Yeah?
You said that the universe is finite. What's that anyway?
Well, I don't know if the universe is finite. So, the universe might be infinite. If it were finite, it would be in much the same way that the surface of a balloon is finite. And I'm going to talk more about the geometry of the universe as a whole, because this is a confusing topic. But when we talk about the universe expanding, you have to remember that it's everything that's expanding. So it's not like it's not like you have something in the middle of the room that's expanding into the room. It's that everything, including the universe itself, is expanding. Okay? So in much the same way that the surface of a balloon does not have an edge, but if you blow up a balloon, it's growing. The surface of the balloon is getting bigger and expanding, even though there's still no edge. That's the way you could think of a finite universe. A finite universe would be like, the area of a surface balloon is finite. It might be very, very big, but it's finite. So it would be like that. So there doesn't necessarily have to be an edge, but it might be that things wrap on themselves. And I'll talk more about this. So the implication of this is that, we have this distribution of galaxies and they're all moving away from each other. Generally everything is going away from each other. So I wanted to spend a little bit of time now talking about how Hubble actually went about measuring these velocities. Okay, I talked a lot about last time about how I went about measuring distances to galaxies, or a couple times ago, where you use the idea that the Cepheid variable stars blink with some rate, and the rate with which they blink correlates with how intrinsically bright they are. If you know how intrinsically bright they are, you can determine how far away they are. And that's one way you get the distances on this axis. But then how do you know what their velocity is? So I mentioned this earlier. The way you can determine velocities of objects in astronomy, you don't just make this up, you can measure it. And the way you measure it is this phenomenon that's associated with the Doppler shift. It's the same idea that if you have a train and it's got a whistle, and you're headed, and the train is heading towards you, the whistle will sound more high-pitched on its way in and low-pitched on its way out. Okay, and that's because the wavelength of the sound, the effective wavelength of the sound, is you're perceiving a long wavelength when the train goes away, and you're perceiving a short wavelength when it's coming towards you. So the crests of the sound wave are getting piled up more rapidly when the train's going this direction, and if you're over here, the crests of the sound wave are getting stretched out as it's dragging on behind the train. The same kind of thing happens with light, except for a light ray, when the wavelengths get scrunched together, they get shorter. That's blue light. Blue light has shorter wavelengths, and longer wavelength light has redder. So that if you're here and you're watching something go away from you, the light emitted from it will be stretched and therefore look red. If the thing is heading towards you, the light emitted from it will get scrunched together, the wavelength will be shorter, and it'll look bluer. So that's called redshift if something's moving away from you, and blue shift if something's headed towards you. Yeah?
Has there been any measurements as far as the distance between the sun and the Earth? From other parts, just too small to scale.
The sun and the Earth. The distance between the sun and the Earth, it changes a little bit over the year because the Earth is going on an ellipse. And the Earth is slowly dragging into the sun, very, 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 very slowly. And I believe that there are measurements of that, but that's outside my field of expertise, so I don't know a lot about it. Like one of the things I do know a lot about, for example, is we measure the distance to the moon very accurately. And we do that with other tricks. So it's not really done with the Doppler shift. There are other tricks that you can do by combining the crests and troughs of light waves to figure out distances. So you're doing a really precise timing of light coming from the Earth to the moon and back. And interestingly, that's done with mirrors that were placed on the moon by the Apollo astronauts. And so the modern measurements of the distance to the moon are still using mirrors that were placed there by the Apollo astronauts. We're shooting lasers back and forth. But anyway, see, I gave you the political answer there. You asked me a question, I didn't really know the answer, so I just talked about it. I'll try to. If you're really interested in that, I can try to find the answer out for you. But I don't know much about current efforts to measure the distance to the sun. Really, really precisely. But anyway, so the main thing, it turns out measuring distances are a lot harder than measuring velocities. And that's something that people have struggled with for a very long time in astronomy. Velocities actually are pretty straightforward, especially when we're talking about velocities along the line of sight because of this redshift effect. And in fact, it's not just that we can tell whether something's headed away from us or heading towards us. We can tell with very high accuracy exactly how fast it's moving away from us or towards us. And the relationship is such that the change, like for example, if the galaxy is moving away from us, then the wavelength lambda will be stretched to a new wavelength lambda plus a little bit extra. That little bit extra is called delta lambda. Delta is sort of change of. So it gets a little bit longer. And so you imagine light gets emitted at 3,000 angstroms, but when you see it at 3,300 angstroms. It's a little bit stretched out. Or if that same thing is moving away from us, the light would be emitted at 3,000 angstroms minus a little bit, minus say 300 angstroms. So now it's at 2,700 angstroms. So it would look a little bit different. And the faster the speed, the bigger this delta lambda is. So it turns out that the ratio of the speed to the speed of light is about equal to the ratio of the change in the wavelength to the wavelength itself. So if you're moving fast, if you're moving a tenth the speed of light, the wavelength will get shifted by a tenth. So if you're moving a tenth the speed of light and the initial wavelength is 3,000 angstroms, you'll get shifted by 300 angstroms or so. If you're moving 5% the speed of light, it would be 150 angstrom shift. And you can measure this shift, and by measuring that, you measure the speed. Are there questions about that? Okay, so this is a technique that people have used, and people have known about this for a while. So here's basically how it works. Let's say you see an object, okay, and the light from that object comes at you, and it spreads out into a spectrum. And you see these absorption lines that I've talked about already. Okay. Now, what I already told you is that we can use these absorption lines to figure out what stuff is made of, because where they get absorbed depends on the type of atom that the light's going through. But it's not just that. Once you see those lines, you know where they should be. So because we know, for example, this is hydrogen, say, we know exactly where the line should be. It's hydrogen. And we know this line should be here, there should be another one there, then another one very close to it, and then this one, this one, this one, and this one. Okay, so we know what the pattern should be. It's almost like a fingerprint, right? But if that same object were moving towards us, all of the light gets shifted blue. So look at this pair of lines here. It gets shifted to the left a little bit. So it's like that fingerprint, except the fingerprint shifted a little bit. And so you know everything has been shifted blue. All right? And by measuring exactly how much it's been shifted to the left, you can tell exactly how fast it's moving towards us. Does that make sense? Are there questions about that? Similarly, if it's moving away from us, the same deal. Instead of shifting this way, it'll shift this way. So it's the same pattern. And by measuring this distance, by how much wavelength it's shifted one way or the other, you can tell whether it's moving towards us or away from us, and with exactly what speed it's moving towards us or away from us. Okay? Are there any questions about that? Okay. So I don't want to spend too much time going over the details here. I mean, it's important. One thing I do want to do is I want to emphasize to you that when I tell you things, or when you see, when scientists, when you read articles and scientists telling you things about how they measured something, it's important to recognize that there are techniques that have been developed to make these measurements. It's not like you can just look with your eye at Andromeda and I can tell you how it's moving towards us or away from us and how fast it's moving. You have to develop these techniques to do it. And so it's important to recognize that there are sort of techniques and tricks that have been developed to do it, and also that it's not easy to do. And that in principle there can be errors there, right? Because you can imagine trying to do this and determining how fast this thing is moving. You got to measure that distance, and you can measure slightly wrong, or you might not have the right lines, So it's problematic at some level to do it exactly right. But over the last 50 years or so, we've really, we spent a lot of time figuring out how to do it. Okay, so any questions about basically what's going on here? This is what Hubble did. So Hubble was able to use this technique, together with his methods to determine distances to galaxies, to show, in fact, that the universe is expanding. So by this careful analysis of what light does under different circumstances, and then applying it to astronomical objects, he was able to determine for the first time in human history that we know for sure that the universe has not always been the way it is. And that it looks like it's changing, it's evolving with time. So the history of this is actually a little bit more complicated. Before Hubble did this, in the early part of the 20th century, there was this guy named Vestal Slipher, who in fact did notice that galaxies seem to be all blue-shifted. Their light seemed to be acting like they're all moving away from us. What he didn't have was a very good determination of their distances. And then Hubble added the additional fact that not only were they all seeming to move away from us, but the farther they were away from us, the faster they were moving away. And it's this thing, the fact that the speed grows in proportion to the distance to us, that really is indicative of something that's expanding. I think I mentioned this to you before, but any system of stuff that's expanding about the center will behave this way. So if you measured the speed of shrapnel from an explosion, the stuff that's farther away will tend to be moving faster than the stuff that's closer to the explosion itself. So it's just a general phenomenon of stuff as it's expanding. Yeah?
Do you have an explanation of why that happens?
Well, for the explosion thing, it's pretty straightforward. It's that the stuff that's moving fastest will just have gotten farther in the same amount of time. So the slower moving stuff stays down here, and the faster moving stuff stays up here. The fact that this is this way is an indicate. Well, we understand it in the context of general relativity. This is exactly what you would get, for example. Well, let me show you a little diagram, and I'll come back to it. Okay, I think I showed you this diagram before, but let me now explain it to you in the context of this fact that the velocity should go like the distance to the object. Okay, so now look at this. I think I told you what I did with this before, but I think it's important to realize just how simple the thing is that I've done. I made these stars with PowerPoint. It took like 4 hours. It took forever to do this. And then I selected all the objects, and then I said expand by 10%. Okay, I copied it, and then I changed the color to red, or purple, and then I plotted that. Okay, so that's 5 hours work. So I'm going to keep doing it. 5 hours took me 5 hours to do that, and then after I did that, it only took me a couple minutes, and then I did that. So then I did it again and colored them red. Okay, so the whole thing is expanding. But let's watch the phenomenon here a little bit. Let's suppose we live on this object. So when everything else is expanding, we stay there. Okay? Because if you live on it and you're moving with it, you don't see it moving. So you just renormalize to that. So now I take those same images and I restack them, but now I stack them all centered on that object. So I just take the same purple, now that one turns purple, and I stack it. Okay, you see what I've done? So now I've forced myself to ride along with this one. And now this guy has to be moved away because the whole thing is expanding. And this guy is moved away. Notice that this guy has moved away more than this one. Why is that? That's because the whole system is expanding uniformly. But there's space here that's expanded, and there's space here that's expanded. And added together, the two together have made this one move more. And I do it again for the red, and the same thing, right? This red point's really far away compared to this one. And this very distant red this very distant red point is moving very fast. The things that are nearby are not moving as fast. As you imagine these as time steps, like a minute, like 1 minute, then 2 minutes, and 3 minutes. In 3 minutes, this guy's moved this far, but this nearby thing has only moved that far. Does that make sense? So that's what's going on. Now, the other thing that you can learn from this thing that took me 5 hours is you can stack on another object. And you can pretend you're an alien living on a different galaxy and ask what they would see. Well, to them, it looks like everything's moving away from them, too. Now, this is the galaxy we live on, and it's moving away from it. Right? Because if I think I'm not moving and I see you moving away, but I could have easily just put myself in the other galaxy and it looked like that's moving away. And other than that, everything else looks the same. The galaxies that are farther away are moving away faster. The galaxies that are nearby are moving away slower. And it's in direct proportion to how far away they are. Because everything's just growing, the whole thing is growing uniformly. So this is exactly what you expect if the whole space is just expanding. Does that make sense? Okay. So we can pick another galaxy and do the same thing. Okay. Any other questions? All right, let me go back. Okay. So this fact that the distances to galaxies are explained by this relationship is called Hubble's law. And this thing that tells us, this h-naught, is the thing that tells us how fast the universe is expanding. The bigger this is, the faster the speeds are for a given distance. Okay, so this thing, this h-naught, is called Hubble's constant. And it turns out that the value of Hubble's constant is intimately related to the age of the universe. So by measuring the slope of this line, which is really what Hubble's constant is, we are constraining the age of the universe itself. Because a simple way to think of it is, if the universe is expanding like this, at some point it was smaller and smaller and smaller, and there's some time when everything was at one point. And that point we associate with beginning, now we call it the Big Bang, and it's how long it took to go from that point to what we see today, that we think of as the age of the universe. Questions about that? So now, this is Hubble's first plot from 1929, and he kept working on it. Okay, so as the years went on, he made other plots, and he was able to take it out to larger and larger distances. Okay, so this all of his original, like this is a later plot from the sort of 1930s or something. All of his original plot was in this corner, and he took things out to very far distances, and he found out that as he went farther and farther away, this is in millions of parsecs, which is sort of 3 millions of light years. As he went out to sort of almost 100 million light years, this relationship just kept going. So as you looked at galaxies that were farther and farther and farther away, you saw they were all moving away from us, and they were all moving away from us at speeds proportional to the distance to them. And the goal, what Hubble's constant is it's the slope of this line. It's the thing that says, okay, well, given a velocity, what's the distance? Or given a distance, what's the velocity? Okay? And so the slope of the line just means how steep is it. And our current best estimate for the slope is given this way. And it's kind of a funny way to give, you might think of it as very, very funny units, but it's about 70 kilometers per second per megaparsec. And the reason why it has those really funny units is because of his equation. You want to be able to multiply by a distance and get a velocity. So if you have something that's kilometers per second per megaparsec, and you multiply it by a distance, which is typically in megaparsecs, the megaparsecs cancel and you just get kilometers per second. What this means is, if the thing is at a distance of 1 megaparsec, it ought to be moving at a speed of about 70 kilometers per second. 70 kilometers per second is obviously pretty fast. So the universe is expanding pretty fast. Okay. So how this works is, oh yeah, this is what I meant to say. So this first plot that he made was all in this corner. And then a few years later, he was able to extend it way out here. And he shows that it just keeps going. Now the other thing that you notice here is that if you notice these points are much more jumbled when they're nearby, and they're a lot more right along the line as you go far out. And that's because very nearby, the velocities aren't always just moving away from us. Sometimes stuff is orbiting around itself. So it gets a little bit complicated. But all in all, stuff is globally moving away from us. So what this means is, because of this equation, for example, if the velocity is measured to be 71 kilometers per second, then the distance has to be 1 megaparsec for this equation to be correct. If the velocity is measured to be twice that, 142 kilometers per second, then the distance has to be twice that, or 2 megaparsecs, etc. Okay. Questions about that? Okay. Now, all right, so now everybody's falling asleep and everyone's getting really tired. We still have a little bit of time to go. So now, just because I'm cruel, I have a quiz question here. I'm not going to grade you on this, but I just want to see if anyone notices anything funny about this diagram. So here's a diagram. This is a Hubble diagram. So remember what's going on here. Someone's gone out to a telescope, they've measured the velocities to galaxies and the distances to those galaxies and plotted them like this. And roughly they all follow along this relationship. That the farther they are away, the faster they're moving away from us. Is there anything else weird? Is there anything weird about this diagram other than that?
Jumbled parts in the middle instead of at the beginning.
Say it again,
So
sorry.
they were supposed to be more jumbled, like towards the base of the axis.
Right, there's some jumble. There's some jumble here. Does everyone see this jumble? Okay. So if this were your lab notebook and you had to turn this lab notebook in, you might say, well, I don't know what's going on with that, but my line goes through it and I'm going to turn it in. Okay, because I got to go. But you might say, you know, especially the really geeky among you might say, well, what's going on there? What is up with this? Because there's some things that are moving, you know, more towards us than they should be. So some things that they're moving a little bit more towards us than they should be, and the other things are moving a little bit more away from us than they should be, based on this general expansion. So what's going on with that? This is the kind of thing you see when you run across a bunch of galaxies that are living in a cluster, that are living together in a galaxy cluster. Okay? So, let's see if I can make this dark. So, if you have clusters of galaxies like this, they're all living together. They'll tend to orbit around each other like a bunch of bees in a hive, and that hive is moving away from us with the expansion of the universe. But all those galaxies are not moving away from each other. They're all circling around each other, like this. And so what you see is that when you have these balls of galaxies that are orbiting around each other, you'll see features like this in Hubble diagrams, because some of them, even though as a bulk they're moving away, within that bulk, some of them are moving this way and some of them are moving that way. So I might be moving this way around the center of the cluster, but the whole cluster is moving away. So some of them, they actually have some a little bit more bulk motion this way, some more bulk motion that way. So what this is it's sort of a bound distribution of galaxies that are all going around themselves. And the reason why I show you that is because it actually is good. It's a good representation of the fact that it's not everything that's expanding in an expanding universe. Okay? Not everything is expanding. Mostly the space in between things is expanding. Okay? So the Earth is not expanding. Right? The distance between the Sun and the Earth is not moving very much. Roughly stable. Okay? It's not expanding like the rest of the universe. People are not expanding. Okay? At least not for those reasons. So that's that's not what's going on. The space around us is not expanding like that. And that's because there's too much gravity here locally to allow the universe to do that stretching. The gravity keeps the space from expanding. So what you really have is pockets of space that are sort of held tight by the gravity of the stuff associated with them. Then in between those pockets, the space doesn't have much stuff in it, and that's the stuff that's stretching. So if you can envision two bowling balls in a really big mattress, they create dents in the mattress, and the mattress is spreading out between the bowling balls. Where those bowling balls sit, they just sit there and move out. So all the galaxies in the universe, and especially galaxy clusters, are little pockets in space-time that are not expanding. But everything else is expanding between them. And it's the space that's expanding, not the stuff in space. Okay. Are there any questions about that? Okay. So let's talk a little bit about different ways to understand this expansion. Okay, so one popular analogy for thinking about the expansion of the universe is called the raisin bread analogy. I don't know why this is so popular because I don't know a lot of people who bake raisin bread a lot, but apparently this is something that you're supposed to identify with this. Okay, so imagine you've got like some bread that you're baking and you've put raisins in it. And as the bread bakes, it expands. Okay, you have this initial distribution of raisins in your bread, and your bread expands, and now all the raisins are farther apart. All right? Now the raisins are supposed to represent galaxies. Now, one thing you can see is, so these two raisins are 1 inch apart. Then the whole bread expands, and now these two raisins are 2 inches apart. These two raisins were 2 inches apart. Since the whole thing grew by a factor of 2, what was 2 is now 4. And similarly, that one that was 3 is now 6. All right? Now, since it took exactly the same amount of time to go from here to here for all the raisins, that means for these two raisins, these things grew 1 inch in an hour. These two grew 2 inches in an hour. And these two grew 3 inches in an hour. So how fast they grow per hour depends on initially how far away they are. The things that are very nearby initially aren't growing apart very quickly, and the things that are far away initially are growing apart rapidly. And this is the same effect with the expansion of the universe. Galaxies that are farther away are moving away from each other faster because there's more space in between them to expand in a given amount of time. Does that make sense? Questions about that? The other thing to keep in mind is the raisins aren't growing. The raisins don't stretch. It's just the space in between the raisins that stretch. Another way to think about it is you have knots in a rubber band. You stretch the rubber band. Same thing happens. Two knots that are far apart get stretched very far apart in the same amount of time, but these two guys that were close together don't get stretched that far apart in that amount of time. Because it's all about the stretching between them. If there's more stuff to stretch, the more it will grow. Questions? And finally, it's the stickers on the surface of a balloon analogy. Okay, so you have a surface of a balloon, you put stickers on the balloon, you blow up the balloon. This is actually a much better analogy to what's really going on. Because unlike the raisin bread analogy, where the raisin bread is expanding in an oven, okay, the universe isn't expanding into anything. It is everything. There is nothing else, as far as we know. So it's just the universe. That's what's expanding. So much like if you were two-dimensional beings living on the surface of a balloon, okay, your world is not stretching into anything. Your world is just growing. And so your two stickers here just grow farther apart. The other thing that happens as the universe grows farther apart is the light emitted from these objects gets stretched in wavelength for exactly the same reason, that redshift. So it's that stretching that Hubble observes, that he observed. When things were farther away, the wavelengths of that light get stretched more as the universe is expanding faster and faster for things that are farther away. So, are there any questions about this? Yeah.
I'm just a little confused. Like, if the universe were a balloon and like galaxies were on the balloon,
Yeah.
and they looked out,
Yes.
what would they see?
So that would be like looking out into the fourth dimension, which you can't do. Okay, so when I say you're trapped on the surface of the balloon, I mean everything. Like, you can't, there's nothing else. You're really two-dimensional beings living in a two-dimensional world, and the only direction you can see light coming from is along the surface of the balloon. You're two-dimensional, you can't look up. There is no up. You're trapped on the sheet of paper, or the surface of the balloon. That's what I mean. So in much the same way, in fact, mathematically, you can think of the expansion of our universe as a three-dimensional sphere embedded in some mathematical four-dimensional space. There is actually no fourth dimension in that sense, but that's just mathematically how you have to describe it. So one of the reasons why, let me just mention this now. So, one of the things, the question I get, if I'm on an airplane and someone sits next to me and I don't want to talk to them, and they ask me what I do, I tell them I'm a physicist. If I do want to talk to them, I tell them I'm an astronomer. Okay? If I tell them I'm an astronomer, then at some point, 20% of the time someone will say, well, what's the universe expanding into? They'll ask me that question. Well, if the universe is expanding, what's it expanding into? The three questions are, what's the center of the universe? What's the universe expanding into? And what was it before the Big Bang? Those are the three easy questions I get. Those are very, very difficult questions, but basically because it turns out that none of them are actually framed appropriately for what we really understand. So, and this is unfortunate, right? So the annoying answer that I always have to give, which I know is an annoying answer, is, number one, it's not expanding into anything. It's the only thing that's expanding. There's nothing else. Number two, with standard conceptions, there was no before the Big Bang, because at the Big Bang, time and space began. It wasn't just space. It was time and space began at the Big Bang. So saying what's before the Big Bang doesn't make sense. It's like asking, what color is the number 4? It just doesn't make sense. So it's a difficult question to answer. And so even though I understand that it's frustrating and I'm giving you this it sounds like I'm being political, and my answer is, oh, well, I can't answer that because it's a two-dimensional sphere. It's actually true. So the way the way that the theories are conceptualized are written down mathematically in general relativity. There is nothing else. There is just this three-dimensional space, and it is just expanding, and it's not expanding into anything else. It is everything. And as far as we know, there is nothing else. There is not another dimension, at least not a dimension the way we think of them, that the universe is expanding into. And so while this is an okay analogy, it's not a perfect analogy because you immediately say, well, why can't I just look up and see this? It's as if, imagine you were a two-dimensional thing that could only see things along the surface and can only move along the surface, and you can never look up. Yeah?
Does that support the possibility of there being multiple universes, or does that...
Right, so the question is, does that support the possibility of there being multiple universes? It doesn't support or refute the possibility that there are multiple universes. The idea of multiple universes is something I'll talk about at the very end of the class. The problem with this multi-universe idea is that, by definition, if it's another universe, it's very, very difficult, if not impossible, to observe. And so one of the things I've strove to do to impress upon you in this class is that everything I'm talking to you about is stuff that we can actually test with observations. That we can do an experiment or look at something and test this crazy idea and see whether it's true or not. One of the problems with the multi-universe ideas that you'll read sometimes in the popular press, if you're into reading that kind of stuff, a lot of those ideas are very difficult to test with real observations. So they're pushing closer to the realm of philosophy than they are to science because of that. There's been recent work in the last year or so that suggests that there might be observational indications of something funky going on with this kind of thing. But it's very preliminary now. So I would say it doesn't promote or refute the idea that there might be other universes that are totally disjoint from ours. Okay. Any other questions about anything? Okay. So let me sort of. Oh, I don't have. Okay. So I want to end with this. So one of the things we could begin thinking about doing then is we have this universe that's expanding. And you can imagine it like a movie. Okay? The idea with this movie is that in the past, the universe was smaller. And at later times, the universe gets bigger. That's what we're seeing, right? We're seeing this expansion. And at even later times, it gets even bigger. So it's this movie that grows. So in principle, you could ask, how long ago was size 0? And if you could figure that out, you would be determining some estimate for the age of the universe itself. You'd be answering an age-old question, the kind of question that people that probably always ask themselves when they look up into the night sky, which is, how old is it? How long has all this stuff been there? Now, the way you can answer this question roughly is actually pretty straightforward. Because imagine your friend lives a mile away, and you're standing outside of your house, and they drive by your house going 60 miles an hour. How long ago did they leave their house? They drove a mile, driving 60 miles an hour.
A minute ago.
A minute. Right? You know if you're driving 60 miles an hour, you're driving a mile a minute. So if they drive by your house, and they live a mile away, and they go by at 60 miles an hour, you can say, oh, they probably left their house about a minute ago. Same kind of idea. If we see the universe expanding at some speed, we can basically estimate how long ago it was at 0. Now there are complications there, because could your friend fool you? Right? Maybe they actually stopped for ice cream along the way or something. Or they were or maybe they slowed down. Maybe they left, 30 seconds ago. Okay, and they were driving 90 miles an hour at first, and they just applied the brake, and then they're just only going 60 here. Or maybe they sped up. They started going 0, and they only just got to 60 when they got to your house. And so you'd be off. You'd be, oh, it's about a minute, but maybe it was 2 minutes, maybe it was 3 minutes, depending on traffic or whatever. So you still get a rough idea, and that's where we are in this lecture now. So next lecture, I'm going to talk to you about a very rough estimate for determining the age of the universe based on this observation that Hubble made, and then how we go from there to get more precision on what the age really is. Okay, thanks.